Okay, so I'll just start. I'll just start 2 minutes early, maybe, because it's a little bit dense lecture. So yeah, I wanted to do a little bit of recap from last lecture. I added some slides. The slide that I shared, it's pre-lecture. So if you see any difference between the slides you've downloaded, I'm just going to upload the updated slide after the presentation. Okay. I think. So we finished off in, the cross attention, and we quickly went through like BART, but I wanted to touch back on the cross attention part and make sure that everyone is, just wanted to recap it. I added a couple more slides with diagrams, so maybe just to give a pictorial depiction. So last lecture we covered the encoder-decoder blocks, and then we talked about how to think of keys and values as filing cabinets, and that kind of real-world analogy. You can also, like, in some resources I've seen people using it as hash tables. That's also like an analogy, but I wanted to use a real-life example, and I think filing cabinet gives you that idea that the decoder is sort of querying for a question, looking at a filing cabinet, and you're looking at the labels on the cabinet, and then you're going to whatever drawer you want to go to, and then you open it up and you look at the values. Okay, so it's a good way to have a real life analogy of it. And I had a couple of questions about like what is the difference between the cross and self-attention. So I added 2 more slides to depict that difference. If you look over here, so basically here at the top is the sort of decoder flow. And the bottom is the encoder flow, where you have the usual, you're getting your key and value vectors, right? And then the query is happening, you're getting the query vector from the decoder here, DQ, and you're doing this cross attention. You always do attention between Q and K, okay? Regardless of self-attention or cross attention. So you do cross attention, and you get this, the matrix, and then you do a softmax, the usual steps, right? So we looked at the steps where we'll always follow this key 4 steps, right? Like same thing in sequence to sequence with attention as well. So we get the query key value vectors, and then we score score between query and key, normalize it, and then do a weighted sum, okay? So going back here, we're doing the softmax, and then step 4 we're getting a weighted sum. Okay. The only difference is that here I've sort of pasted that self-attention slide again. So when you're doing self-attention, you're just doing it with the same, the same K, Q, K, V, all are coming from the same source, sort of like the encoder tokens or the decoder tokens, right? So the attention is again between your query and key matrices, but here it's self-attention, and here it's cross-attention. So not much difference. Now note that because it's coming from, like, the dimension could be different in this case, because the number of tokens, right? So basically, let's say if you have 10 French words, and then you can have 8 English words, so they don't have to match, right? We understand that concept. So apart from that, everything else is the same. Okay, I hope it's clear. And then we didn't talk about the drawbacks of transformer. We described, well, we sort of did, but we didn't have any slides. So I wanted to talk about some of the drawbacks of this architecture. So in the current framework, we're very much going down this path where everything is transformer based, and the improvements are sort of improvements in the various components of the transformer architecture. So today's lecture, I also wanted to sort of showcase some other new ideas where, to think differently, because yeah, there's a lot of research happening, but it's still in that path that, okay, we have this canonical transformer architecture, and then these are the problems. So one problem we talked about is the quadratic attention cost of the attention mechanism, right? So I hope this figure makes sense to everyone. So we have the query and the key, right? This is the computation block that's very expensive, because you can imagine that we have this quadratic, like it's growing quadratically with your input sequence length. So yeah, we'll look into the different ideas. I mean, I don't think it will be like tested, but I just wanted to, especially for grad students, if you want to think differently what's happening now, I think it's a very cool new directions that's happening. But here, oops. Okay, good. So I wanted you to pause and ponder for a second that why this could be a problem. So think about it. Even when you're inputting something, I don't know if you've used the OpenAI GPT API or any other, like you're prompting the language model, you have a limitation on the input size, right? And that limitation is coming because of this. Because as you increase the length, like for the computation cost is growing quadratically, right? So this is very limiting. As an example, say our dimension D, say it's like in modern LMs, it can be thousands, in the thousands range, but even if it's, let's say 1,000, and if you take a sentence length between 10 to 30 word tokens, then your computation, like, every time, you want to have multiple sentences, like it's scaling quadratically. And usually that's why you'll have a kind of bound set on max tokens, like 512 tokens. Now it has gone up, and we'll probably talk about it, but those are improvements, but this is a like classic bottleneck, right? But then it's a problem because we want to process, what if we want to process larger documents? We want to process a whole document which can have many, many sentences, right? This is an active research area that's still in that pathway of we have a canonical transformer architecture and we're trying to improve on it. There's a lot of papers like row former, flash attention, sliding window, most of it focusing on how we can increase, how we can make this attention mechanism more efficient. Another drawback or another area of improvement is the positional encoding, right? So we looked at the vanilla positional encoding, where we're taking absolute position of each index, and then we were imbuing some representation using sinusoids, right? That takes a function of like the index position and the dimension. So this is a very computationally heavy way to represent time. And there's been a slew of works that focuses on improving this positional encoding improvement at a high level. At a high level, the idea falls under this relative position encoding. So instead of saying absolute position, can we induce some kind of relative positioning, okay? So if you take this stop equation as the canonical vanilla model that we see, where you have like, the QKV, our three query K value vectors, and then we have this index I. It's very much dependent on the index I. Here, PI is like positional representation and positional encoding, then it's always like it's an absolute position PI, right? When we move to this relative position encoding idea, you can see that the P has a little bit of, has a tilde on top, which what it means is that now we are learning this position. We set a relative position between the two, let's say, query and key coming from encoder decoder, and we learn that relative positioning. So that is the key idea. I mean, that we're not going to go into the details of these techniques, but I just wanted to have the notion of like what's the new direction taken. This is this is in that vein. This work is rotary position embeddings that has been adopted in most modern LLMs, and most LLMs use this embedding these days. And the idea is the same thing, that change the absolute position with a rotation matrix. And again, we're not going to go into the details of the implementation, but I want you to look at the results. You know what blue is, and they compare it against like transformer, which is the model that we saw. And the idea of the results are that you can get comparable results, but you don't have to do absolute position encoding, okay? So relative position encoding works, and it is more efficient in terms of like training and results, and so there's no reason for us to not use it. Yeah, so this is an aside slide, but if you're interested, please read this paper. I think it's a cool paper. Okay, so we talked about two drawbacks, and we talked about sort of the main bottleneck of improving on the other side, that how can you improve the attention mechanism, right? So here, again, this is going to be a side slide, and this was thanks to Daniel, who shared this slide deck with me, and I wanted to give you this idea. I mean, don't like being a, you know, even if it's too confusing, or like I'm just telling you, it's not going to be tested. So the problem, as I said, was that, you know, now we're scaling up, and how can we improve the context size or the attention mechanism, or this computation bottleneck? So this is sort of what I talked about. The quadratic scaling in sequence length n this is a problem. So the current, if we stick with this transformer parameter or the attention mechanism, then we are stuck with this paradigm lock, right? So we can think of ideas to improve this, like the components, but can we think completely differently? And this is where I think the newest trend, the gem-based architecture, that comes into play, that tries to look into attention-free architectures. Again, I don't want to, I mean, this is the goal. I'm just going to give you a preview, and we can, if anyone's interested, we can talk offline, but we're not going to get into the nitty-gritty details, technical details of how it's implemented, but I'm just going to give a high-level idea of how it's done. So basically, like, and in order to like really get into the details, I have to also talk about how GPU does computations and GPU blocks and threads, which I'm not gonna, this is besides the point of this lecture, so I'm not gonna get into it. But the idea is that, like, if you look at the left, so we're trying to get rid of this attention architecture, and then, so what we do is that we sparsify the MLP, and think of this one as a way, like this is better for GPU computation. We're sparsifying the MLP, and trying to work with diagonal matrices. And then this on the bottom left is where the authors, they propose sort of gated convolutions as a replacement for attention block. And when the Moner mixer, a recent paper, what it does is that it just combines this, this attention block is replaced by this convolution-based model, and then the MLP is replaced by subquadratic, this diagonal matrices, and that's the high-level idea. And it shows very promising results, scale subquadratically in context length and model dimension. I mean, the results are really impressive. So yeah, it's a new way to think about it, getting away from attention architecture. Okay, so, but since we're talking about transformer, I mean, Moner mixer hasn't reached that state. Maybe that will be covered more in detail in next year's iteration of this course, who knows. But let's get back to our familiar paradigm, which is the transformer-based language models, okay? So we talked about, like, there's three main kinds of variants: encoder only, decoder only, and encoder decoder. And I think we looked at BART, the encoder only model, and the encoder decoder. We touched on T5. I'm gonna do a quick code demo for you today, and that relates to the assignment. And it also sort of encourages you for you to have some ideas of optional bonus points if you want to do it, or how, if you're a grad student, if that interests you, or like any research interest you may have. But before we do that, let's quickly go over, recap what we talked about. So we know how BART works, and we talked about the masked LLM training, and so the so-called Bartology papers, which shows what the heads are paying attention to, etc. And some limitations of BART architecture or the BART model, like pragmatic inference and in terms of world knowledge, and semantic knowledge, and syntactic knowledge. You can read this in the slide. So we didn't talk about why BART was so popular, or why BART mattered. So when BART came out, just not only, like obviously the results are very impressive, but at that time the benchmark results on glue and super glue, it was actually outperforming human performance, right? So it was very, it obviously generated a lot of interest that, like, you know, these models are doing better than expert humans even on certain tasks. So this was sort of like a paradigm shift. And besides the performance, it was really good at different tasks. So it was versatile, meaning that off the gate, you're getting this pre-trained language model that, okay, so you just pre-train a block, and then you can use that pre-trained block for many different tasks, okay? So you take that and you fine-tune it on whatever your downstream task is. So this versatility sort of really introduced this notion of pre-train then fine-tune idea of like transfer learning, right? So at scale. So, excuse me. Whoa. Okay, so I can cough. And then, but still then, you know, just encoder-only architecture, did that mean that, you know, we could just use BART for everything? The answer is no, because there are certain tasks that involve like generating sequences autoregressively. For those tasks, having a decoder architecture is preferable, right? So you can use that in conjunction. So think about the problem of we're facing. We have to do machine translation, and if you had like just BART, how would you use BART for doing machine translation? And so the thing is that you can still do it, but it's preferable to do it because we're generating one translated word at a time. So maybe having a decoder block is more amenable to our purposes. So and then, you know, the variants of BART showed this, and this is a recall slide. So you have the BART architecture, BART, where you're basically still using the pre-trained blocks, right? You can use those pre-trained blocks, but you slap some more parameters that you train to your sort of the SIG-to-SIG machine translation paradigm. We saw French coming in, English out, and you train it the way we did for encoder-decoder. So encoder-decoder architectures is better in certain tasks. And yeah, so BART was very popular and successful because of this thing that you can use that pre-trained block for many different tasks. And we talked about T5. So T5 was another, it's basically the standard transformer architecture with more systematized version with like clean data, more data, lots of experimentations on the architecture. They did you know, test on decoder only, encoder only variants of T5 structure, but at the end of the day, it's the best performing was with the denoising objective and encoder-decoder model. And we talked about the MLM, we talked about span corruption. So instead of the familiar word, fill in the blank or find the word, now the corruption is like over a span, and then the prefix LM sort of masking, right? So we talked about this. So you have this prefix which can sort of denote the task that you're trying to do. Now, think about one cool thing. So the whole idea of this paper was that now they propose any problem. So before you had translation, you had word sense disambiguation or summarization. Now, if you have that prefix, so then you can sort of propose any task as a text-to-text problem, right? So you say that, okay, I want to do translation. So then translate French to English and then whatever, give the input. I want to summarize, then you can say summarize and then give the input. So that was a really cool idea. So that's why, I'm sorry, I don't know why I keep losing feed. I gotta be more gentle here. Yeah, so why T5 mattered? Because you know, you can do a slew of tasks by just using it as a text sort of prefixing or prompting, right? So you're sort of seeing the idea of prompting that we're gonna segue into forming here. Okay, so it unified all NLP problems into one text-to-text format, which is a really cool idea, and then which allowed the same model, loss function, hyperparameters, etc., across the diverse set of tasks. And it was remarkable that T5 could be fine-tuned to answer a wide range of open domain questions. So it performed very well on open domain data sets like natural questions and then trivia, QA, etc., sort of question answering data sets, which showed that you can retrieve. Yeah.
What can T5 do that other models like BERT
Yeah, so basically, because first of all, size is one thing, and other thing is that while you're training, T5 training, it also includes the sort of prefix into the training, and it trains on a diverse data set, right? So with the prefix, with different kind of tasks. And it was also at the time, it was like larger compared to BART and other models. So at the time, you know, so we'll talk about it. So sort of as we grow larger and larger, this emerging abilities are coming into play. So consider like T5 is much larger. At its time, it's a large model, right? I think it's like, I don't know, 11 billion parameters in a billion parameters. So it's emerging. The idea is emerging that now like put everything together in a large model, and we're seeing this prefix LM. And remember, BART wasn't trained with prefix masking. Like it's a different training loss objective, right? So it's not a fair comparison.
Yeah, I'm just trying to understand, like in real life, like if I'm going to choose between one and the other, like how do I know, oh, like with this application, T5 performs better than everything else?
Okay, so for everyone, the question was that how do I know which model to choose? There's some more inputs required to that question, but it really depends on what task you're trying to solve, right? You have certain generic model performance on certain tasks, but if you're comparing, for example, if you're given the choice between should I choose, let's say, a 70 billion llama model versus under billion BART model, which one should I choose? That's not a fair comparison, right? So you have to say that in this class set. Okay, so yeah.
This one specifically though, like what is the competitive advantage of T5 specifically?
Compared to what?
Like when do you use it? Like, kind of like why does this slide exist?
Yeah.
What's the purpose?
So it can do, let's say, okay, so we'll see a demo. So we can do machine translation, and we'll see a demo, or we're only going to see T5. So you can do it using T5, or you can use BART as well. But T5 is, yeah, it's larger, it's performance. I mean, comparable, but I mean, it's a large, so you can use whatever you're using it for. Why do you use it?
So you're saying you could use like this the same as like BERT, but this one is more performant and like let's
oh, I
say
see.
in memory.
Okay, yeah, so so I see. Okay, so for BART, you'd have to remember you have a pre-trained BART, but it doesn't know how to solve any task. You have to fine-tune it on specific tasks. So let's take, let's say summarization, right? So if you take a pre-trained BART, BERT, it's not gonna work off the gate. You have to fine-tune it with some downstream tasks. But with T5, you're getting that capability off the shelf. You prefix it with summarize and then put an input and it works. Oh my. Okay, so just to make my point clear, I'm just going to do a code demo. So it's in your assignment I think in the analysis section. So what I've done is essentially you are going to be using Hansard, and I've taken T5 base. And since this is an applied course, I think this is kind of important that you know how to do it. Like, how many of you have already used Hugging Face or some of its libraries? Yeah, it's a fair amount. So you can basically take a model from there, and with just with a few lines of code, you can test it out. So let's see. Okay, so no, okay, so basically we're gonna, so if it's a data set on Hugging Face, and you can see that you have the split, strain, and test exactly, right? So you go there, you have the data set, and we're just gonna, and if you haven't seen the Transformers library or the Hugging Face in general, it's basically a repository for data sets and models and whatnot, right? So you can just get it from there. And you can simply like click on this, and you just need 2 lines to load this data set, okay? You import the datasets package and load dataset, and you load this dataset. And once you've done that, So similarly, we have here a T5 small base model. You can also look up the T5 base model. T5 base model trained on the Hansard data set. And you can even just put in an inference sentence over here, and that's going to do the translation. So so just as an example, let's pick a large sentence here. All right. Let's do test. I'm just picking a random French sentence, and I go back here, I paste this, and it's going to load the model, and at the same time I'm going to do the same thing for, oh, I think I already have an example here. So Mossier, le president, blah, 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 blah. I have a simple question for my colleague, and I have a different sentence over here. No roots have been a problem and need repairs. Okay, so does that make sense? So that's the idea, and in order to do that, and in code, it's basically this. You can load the data set, and so once the data set is loaded, it's basically a dictionary object with your train and test. And you can further do split your train set with, like, into eval by calling a train test split on it. But essentially, yeah, that's it. You've loaded the, and for the model, you don't even need the data set. I just loaded the data set to show you that you can load the data set, and you can also randomly sample anything from there. So translation using Hugging Face models. So you can just load any model. Like, we're gonna load this T5 small model that's been trained with Hansard and the tokenizer, and then we can load like a random sample from the data set, okay? And then you get a pipeline which is like translation from French to English with the model, and just put whatever text you want to translate, and you get the answer, okay? Now, here I think you can, in the pipeline for T5, you can see that you can actually prefix it with what kind of task you're trying to solve. So both, like, translation is a text-to-text generation. So text-to-text generation is an umbrella term for translation, but instead of here, I could have said like summarization. That would be a different task, okay? So it is this simple that you can basically go to Transformers, and on your computer you can just play around with it and get different translations of. And you can do this for any model. Like, it doesn't have to be this. So for example, you can ask the question that let's say, what is the effect of dialect on these models, right? So I've trained this using Hansard, but there are lots of models that are trained on French data sets, right? So you can take one of those French trained models and then feed in, let's say, Canadian French, like Hansard input, and see the output and maybe see the difference. Now, one thing to note is that data set size-wise, like Hansard is relatively very small data set. So you have to keep it in this mind, but still, see, the thing is T5 base already pre-trained with lots of other data, right? So it has that imbued knowledge in it. But anyway, let's go back to the slides, but I just wanted to show you that you can, how you can use Hugging Face to do this. Okay, so we talked about encoder only, encoder decoder. Now let's talk about GPT series. So here are the first three papers, and starting with JPT, and architecturally they're mostly similar, but each iteration has some more bells and whistles added to it in terms of like, you know, training, data, etc. But architecturally it's very simple. It just uses the classical language modeling objectives. So which is you're trying to predict the next token based on previous tokens that you have seen, okay? And if we, like specifically, the loss objective is something like this, the same LM objective. You're trying to maximize the LM objective, okay? And it's auto-regressive, meaning that it's conditioned on what it has seen in the before. Distinguishing features, so think of this as with BART, we say that think of the transformer model, cut away the decoder piece. Here, you're going to think of it just the decoder piece. You're throwing away the encoder piece, okay? And yeah, so on that same vein, you know, the main difference, it's a decoder-only block, but the block level ideology is the same. Few other models that uses the same idea of being auto-regressive model, like Transformer XL and XLNet. Now, I want to talk a little bit more about GPT-3 because I think this is where LLMs, the idea of, you know, increasing like large and large models, that idea takes off. Yeah, and the idea of like, you know, in-context learning. So with GPT-3, I'll show the slide like in a second, but the idea was that as you increased the model size, this phenomenon called in-context learning started to emerge. So what is in-context learning? In-context learning is something that you can learn to do a task even without learning in the normal sense. How do we learn generally in machine learning is that we do some gradient updates. We do backprop to learn. So we feed in some, you know, whatever data, and then we backprop and we learn. But with this very large models trained on very large data set, it seemed that it didn't have to do it. So, for example, in context learning, so you can provide it with some, you know, examples, and just from that pattern, it knew what to output next. So, so here's 3 examples. Let's see, this one is machine translation, right? So if you're feeding in some example of like thanks to merci, hello to bonjour, some examples of like English to French translation, and from this context, it learns that if I'm fed another English word, I want to output what I've seen before in the in context. So, and this was something that GPT-3 was a canonical example of a language model that started showing these trends, right? At that time, it was 175 billion, which from our previous context, T5 was 11 billion to like 175 billion. It was a huge jump. And they do extensive, I'm sorry, I don't know why every time what's happening? So I remember that at that time I was, I did a like an in-group reading group presentation on GPT-3, and just like putting in GPT-3 in Google resulted in like hundreds and thousands of examples, including one from I think Tom's Hardware, which was really funny. But the point is that it really permeated. It broke that barrier of like, you know, LLMs in academic or industrial setting to the public zeitgeist, right? So it was like a mainstream thing. And ChatGPT obviously magnified the whole thing into a different level, but I think GPT-3 was the first time that that trend really took off. Everyone was talking about it, and it was really like a mainstream thing. So, and this is also where the notion of prompting begins. And we'll be in the next lecture, we'll be talking about like prompting and so what is in context learning. So that means that what you fit to the language model, as an example, you can get it to do tasks. So there's a notion in context learning. You have the notion of zero shot, one shot, and few shot. In context learning setting, the shot means how many examples are you giving it. So for example, zero shot is this: translate English to French. You give it an English word. One shot means translate English to French, the task description with one example. Sea otter translate to l'otter de mar, right? Okay. And similarly, few shot means you're giving the example. So in a paper or anywhere, if you see that, oh, the model performed this with 5 shot value, meaning that it was given 5 in context examples. Does that make sense? Okay. And I think this figure is a little bit too small. So, okay, and this is a slide that depicts how size is coming into play. So we have been seeing at like T5 and whatever in this range, and when you increase the size, like this natural language prompting thing, few shots. So at 175 billion parameters, so that's a huge jump, more than like 120 more billion parameters. We can see this emerging this in context learning paradigm starting to appear. Okay. Okay, I'm not going to move from here. And I'm going to punt the details of it's more like a technical paper with lots of pages, but the results they tried on many different sizes of the models, and as you can see from here that as the size increased, then it had some certain advantages like in context learning results, and overall performance of the models increased. The generalization to out-of-distribution tasks. Some of the training data sets that was published that they used were Common Crawl data set, which is nearly 1 trillion words with quality curation. Another thing to note is that these days, papers are increasingly less interested in divulging what training data set was used, because I guess they don't want to get sued down the line for, but at that stage, people were disclosing. So, and there are also web text books 1, 2, and English Wikipedia. And I want you to understand that from like few lectures earlier, that these models actually learn whatever is in the data set. So there's, and I think you'll learn more about it in the ethics lecture, the importance of having what you feed it to, and the biases, inherent biases, etc. in it. And the training time in terms of clock time, for example, the largest model, close to almost 1,000 days of clock time. So each of these models, they take a very long time to train. Yeah. And the results wise, a lot of results are different tasks, different data sets, but if you distill it, the main 2 key points are unprecedentedly impressive results across different task domains, generalization, and performance generally increases with size. So if you increase the size, there's the performance goes up, and you see this emergent abilities like in context learning. So it set up the trend of training language models that are larger and larger in terms of parameter size. However, there are certain scaling laws which we'll see in a bit. But in general, GPT-3 really started off this trend. Okay, so I think that's where we should conclude the Transformers discussion. I wanted to quickly talk about, again, different directions. So are there, so one thing we looked at, all these language models uses, the tokenization, the concept of tokenization. So we're still doing, if you want to train, if you want to test, the first thing you have to do is you have to, whatever input output, like you have to tokenize it into some notion. But what I'll ask you to ponder is that, what is the idea of tokenization? Like the tokenization, you can tell me that, oh, you're doing word by word separation, but what is a word? Like that is something that we're feeding it, right? That's a construct that we have made. But can we do this without imbuing any of our own construct? Can we just do now, like let's say unsupervised fashion, just give it like whatever we see and feed it to the model? And that's the idea of token-free models. you don't delineate or you don't do any tokenization. You just feed it to character and you get the output to character. Some of the advantages is that you can just feed it the raw text bytes or characters directly. That removes all the whole pre-processing pipeline, right? So you don't have to And what is the problem is, given if you're using transformer architecture, we're stuck with the compute problem, because if you feed a sentence that's 10 tokens, and now you're feeding it like 10 times if you convert those words as characters. So that's a much longer token sequence, and we know that the compute scales quadratically with the token size, right? So that's a problem. And it's also good to know that some of the problems of the pitfalls of doing tokenization the way we do is that we're very much dependent, or we're affixed to this notion of vocabulary, right? So every language model we train, we have to first create our vocabulary, which defines what are our primitive words in that language, right? So for your assignment, you'll be doing like you need to do English and French vocabulary, and then you have mapping matrices. So these are hand-engineered and language-specific strict tokenization, and we looked at segmentation algorithms. You have to do byte pair encoding for various language nuances, right? And then heuristic string splitting, which goes back to the morphology or anomalies between different languages. So you have to use some kind of heuristic rules-based knowledge to apply to different languages, which doesn't have one-to-one mapping, and they can be agglutinative versus other forms. So that's a problem. And it's also, because of this limitations, it's also very brittle to noise. So if you make one typo, then you're making a word out of vocabulary, right? So we have to think about it and install the mechanisms to handle those things. And then next to I wanted to present just one token-free model, but this is again a side, so this will not be tested. At a high level, all these token-free models, there's another one by T5, which is a variant of T5, but without tokens, like byte-level T5. The link is in the website. But the high-level idea is this. What you're doing if you're feeding in just the raw text, so then you have large sequence length. So you'll do something to downsample that. You basically shrink the input size and downsample, do some computation, get the result, and then upsample to the answer. That's sort of the general intuition or idea. Oh. Okay, so again, this will not be tested, but at a high level, very quickly, what you do is you do character embeddings, Unicode embeddings, you do some downsampling to make it manageable, and then you get the answer, and then you upsample to get the final answer. So that's the idea. You can read more about it in the paper if you're interested, but we're not going to talk more about it in this lecture. So I think that's all for the transformers, and since we have a little bit of time, let's also get started on large language model slide. We'll finish it off next lecture, which is after the reading week break, okay? Any question? Yes?
Yeah, just regarding what you were talking about with token-free models. So, there's two things here, right? There's tokenization, which is taking an input string and delineating what the words are. But then there's also vectorization, or whatever you want to call it, where you're using the word to vector something. Which you normally feed into a language model. So those are kind of two separate things. So those you were talking about sounded like basic kind of both, right? You're just literally doing, you said byte.
So you're taking, so think about Unicodes, right? So think about how you can use, if you use Unicode, you can represent almost all the languages in the world, but in basically a much shorter, how many characters are there in a Unicode, whatever, 1,000, 2,000, 3,000, I don't know the exact number, but the point is that your vocabulary, that's your vocabulary, right? Each Unicode character, that has shrunk so much, right? So, but that also allows you to represent a diverse, any language, any emojis or whatever, you can do that, right? So then your question is, with token level, you're doing some kind of vectorization, and you do the same thing, but you do it at a character level, right? So that paradigm hasn't changed. So you just think of your character as one token. And why can't you do like some kind of, you can do a vector representation for that if you wanted to. But the problem that becomes is that I eat rice, instead of 3, it becomes 15 or something. So it's a large, that's the problem. Yeah. Or character or byte level, like however you want to think of it. Good question. Okay, so so I think it's a seamless segue in the sense that we saw that how with GPT-3 people are interested about, okay, so if we make this larger, we get all these advantages, so let's make this larger. So that trend, and then what are some of the implications and how it's been scaling, and are there any scaling laws? Can we formalize that? How big can we get? Is it just about increasing the size, and if it is, then how does it scale with everything else? So we'll quickly talk about that. And yeah, so then we're going to talk about how do we, like, the ChatGPT. So is it like, how do we get from this really large models to getting a language model that can follow instruction? Okay. And then next lecture, depending on the time, like we'll talk about more LLM stuff, like, yeah. So yeah, so if you can see that the trend, I think we talked about Elmo, right? So the contextual word embeddings from that stage, GPT was 110 million, and then it's been, and this slide is like, it's only shows till 2021, but the trend is growing, has grown upwards. And this is a very distilled form, but in the ethics lecture, I think Steve will talk a lot more about it, but is it like, what are some of the cons of just scaling? One is, the democratization of the computation power, and also the social impact, which is like commoner's tragedy of the commons, because it's wise to know about it, and if you're like, be conscious about it. That training burden GPU is roughly equivalent to a trans-American flight, so you can imagine if it's models that are in the level of billion parameters, how much energy is being used. Okay, so this paper, Kaplan in 2020, so they did a systematic review of scaling laws of LLMs. So, essentially say that the 3 scale factors are compute, which is denoted by C, the amount of compute C used for training, data set size, which is denoted by D, and model parameters, which we've been focusing on. Larger means larger model parameters, the number of model parameters excluding any embeddings. Okay, so as you can see that this kind of scaling, performance of transformer-based LLMs sort of have a parallel relationship with these 3 scale factors, CDN. And other hyperparameters or parameters like depth, width, etc., architectural variance does not matter as much. So it was shown that like it improves smoothly when factors N and D, which means the parameter size and data set size, scaled up in tandem. So otherwise there's a diminishing return. So basically you can't just increase the parameter size alone unless you have more data to feed it to train. So let's say if you're training a GPT-3 model, 175 billion parameters with Hansard data set, as opposed to a T5 data set, you're not going to get much of an improvement, right? Because you're basically, GPT-3 is going to memorize the data set, but it's not going to do anything. So you need the data set size, or the number of tokens that you use for training has to increase as well. And roughly, they propose that 8 times model size increment should match 5 times data size increment to avoid performance penalty. And also the transfer learning. So out of distribution generalization depends almost exclusively on the validation loss performance that improves with scaling factors. So if you look at the right-hand side curve, you can see that larger the model, I think the yellow line is yeah, so from blue to yellow, the size is increasing, have a much better, and tokens processed is the dataset size, so has a much better performance than smaller models with which are denoted by blue curves. So at the same number of dataset or the tokens processed, you can see that you have a much lower loss curve for the larger data sets, which also shows that large models are more sample efficient than small models, reaching the same level of performance with fewer optimization. And then the idea of projecting LLMs as foundation models, meaning that the trend that we saw was that the pre-training paradigm continued. So you have certain data sets and you train it on, you get a foundation model, and then you fine-tune that, or you use that pre-trained model for whatever your downstream tasks are, right? And yeah, so this paradigm obviously gives rise to certain social impact things that we need to talk about, right? Like we talked about democratization and gap between industry models and community models, etc. And I'm not, yeah, we'll talk more about it in the ethics lecture, I guess, but these are certain things that you can think about. We're not gonna have time for it. So yeah, okay, so I'll leave you with this thought that that's fine. With GPT-3, we know that we got larger models, it generalizes better. But then how did that paradigm shift happen? How did ChatGPT happen? What is so different about ChatGPT that sort of, again, made that leap into public attention and performance and interest and efficacy or general powers of LLMs? The point is, so next lecture, we're going to start with LLMs to assistant chatbots, and we'll look into how, because if you just take this large LLM and if you give it, if you just ask it that, can you group these words into whatever, it's not following instructions. So what we need to do in order to turn our large language model pre-trained with lots of data into ChatGPT, like instruction following chatbot that actually follows our instruction. We have to do the paradigm, we'll talk about the paradigm of instruction fine-tuning, reinforcement learning from human feedback, and yeah, variance. So that's where we're going to start next lecture. All right, thank you, and have a great reading week break. I'll see you the week after.